to write this down. Let me try to unfold the notation for you. So, but you see, it's almost, I mean, you see, it's really close, right? Like the naive one would be that the actual difference of the map could be captured by the differential acting on the difference. Differential at a particular point acting on the difference, and we just can't do that. It just doesn't happen that way. But we can replace it with the length of the line segment with respect to this zero norm, and then the maximum of the values of the derivative. All right, so the question is, how do you define the maximum? What does this norm of f prime of x mean? See, we haven't defined that. We haven't defined that either. These are from Edwards. All right, so let me show you how that goes. So first of all, here's his definitions, okay? Come on. Definition, x sub 0, it's simply the max norm. It's the max of the absolute value of the first component, second component, nth component of x. So you take the maximum. This is also known as the soup norm. All right. So the unit ball for the soup norm, Edwards has notation for that. He calls it the cube, the 1 cube, C1n. That would be, see what that would be? That would be x in Rn, all right, such that the soup norm of x is less than or equal to 1. So he says, he describes it as this. It is symmetric with respect to the coordinate planes in Rm and Rn, and it has the point 1, 1, 1, 1, 1, 1 as one of its vertices. So now he also has the cube of radius r in n as x in Rn, such that the one norm, right? Excuse me, the soup norm is less than or equal to r. And I think I could, I think without, I don't think I'm wrong. I don't know why he doesn't write this down. I feel like he could. Well, his picture, in fact, suggests it on page 173. But this is literally just minus r to r, minus r to r, and n-fold times. So that's the r cube. That is, though, literally a ball. It is a ball in the soup norm. So a cube is a ball in the soup norm. And that is the thing that would play, something like that plays the analog of a to b. Remember I said we need something that's like the closed interval a to b? It's going to be that, something like that. And, excuse me. So. That's one thing. And of course this is the, that's centered at 0. You can see we could center it somewhere else, right? You just, these are centered at 0. If you wanted to center it somewhere else, you do x minus the thing, All right. And then it becomes, then I cannot just glibly write it as the Cartesian product of an interval, Okay, then check this out. The norm of a linear mapping is by definition the following. If L is a linear mapping from, say, Rn to Rm, then in Edwards, he defines the norm of L, all right, is equal to the max, check this out, of x in the boundary of the unit ball of the absolute value of L of x. Excuse me, not the absolute value, the sup norm of L of x. So it's what I was talking about. He's defining the length of the linear operator by the values the linear operator takes on the unit ball. But he's using the unit ball with respect to the sup norm, which makes it really, really simple how this norm relates to like the entries of the matrix of L. All right.
So the length of the function is
So like here's a thing we can write for it. If you have L of x over the norm of x, sup norm of x, all right? That is by construction less than or equal to the norm of L, right? Since this is something, it's in, the boundary of C1, right? Because it's a unit vector, okay? And if this is true, well, this implies, among other things, that the sup norm of L of x is less than or equal to the norm of L times the sup norm of x. So we had formulas like this that were built on different considerations, but this is pretty slick. See, because this allows you to judge the length of the output of a linear operator simply in view of its norm times the norm of the input with respect to the sup norm. We found much the same, but we did not. We were not as clever as this, yeah? Okay. Great. And he has a proposition, prop 2.1, which is just 2.1. He said that the norm of L is the least number m such that the sup norm is less than or equal to m times the norm of the sup norm of x for all x in Rn. All right, fine. So he also has the following lemma. This is lemma 2.2, which is this. If you have L has component functions like L1 LM, right? A mapping from, let's say, Rn to Rm, okay? Then guess what? The norm of the ith component function is less than or equal to the norm of the whole mapping. That's pretty clever, right? I'll write down the proof for that because I think it's instructive, like just how these things work. Yeah, okay. So you have the norm of Li, which is equal to the norm of Li my bad. Okay, so let me explain here. This, all right. He says, let x naught be the point. The point in the boundary of the unit cube such that Li of x naught is maximal. Why does such a point exist? Well, we're dealing with a continuous map on a compact set. See, since the L sub I is linear, it's continuous, and since this is a compact set, it's closed and bounded in Rn, therefore it attains the maximum, which means not only, there has to exist a point in here that actually attains the maximum. Let x not be that point. Okay? That's what's going on there. And then that is less than or equal to the max of the absolute value of L1 of x naught, comma, Lm of x naught. All right. I mean, that's just a sort of a dumb thing. I mean, yeah, of course, it's a finite list. this is something in that list, but it may or may not be equal. I mean, it could be even bigger. But that is, by definition, equal to L. That is L of x naught. That's the sup norm of L of x naught. That's what that is. Which is less than or equal to the max on the x in the boundary of the 1 cube, the skin of the 1 cube, if you like, of the norm of L of x naught. Okay? And that is this. All right, so there's that. And then he defines the norm of a matrix. Okay, so like his norm of a matrix. What's the norm of a matrix? The norm of a matrix is equal to the max of the sum over, well, it's the max over, I should just say the max over I and j. Oh, no, I'm wrong. It's the max of the sum j equals 1 to n. Max over I think, of j equals 1 to n of absolute value aij. So let me just say it's the max of this such that I equals 1 to dot 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 n, I believe. Oh, m. Yeah, it's the rows. So it's the max. It's the max of the.
Why do we define the norm of the matrix like why the rows?
I mean, that's what he does.
Okay.
And the reason for it, the reason for doing that is that if you follow it through, let me just show you. I'm running out of space here. Okay. All right. So. Why am I using that? It's all yucky. Now my shirt is yucky. Rats. I guess we didn't really need to prove Newton's theorem. Newton's thing today, I just like to show people that because I think it's cool. I know it's calculus 1, right? But it is nevertheless interesting. And it does have I do think it has like essentially a generalization to higher dimensions. So let's see here. So if he talks about the let's try this again. If we have x in an Rn, the one norm of it is just the sum of the absolute values of the components, okay? He's got so many different things rolling around here, you know? He's got the sup norm, he's got the one norm, there's other places, he's got the Euclidean norm. He's got all the norms in play. And so with this notation, the norm of the matrix is exactly the maximum, like you said, of the row norms. Well, it's the maximum of the one norms of the rows. So it's like row 1 of A, norm 1, right? Row 2 of A, norm 1, and then so forth and so on down the line, you know, row, however many rows. I guess there's m rows for us. M by n matrix, right? So yeah. But his point is that this essentially makes our m by n equal to rmn with the with the norm, you know, given like that. All right. So it gives us a kind of peculiar norm on RMN, but it's nevertheless a norm. And so then, let me just show you part of the reason. Here's why he's doing this in part, is like if you have an example, if you have L of XYZ equal to x minus 3z, and then 2x minus y minus 2z, and x plus y. All right. Then the norm of L is simply the maximum of, so you just look at this and go 4, 5, 2, it's 5. So our approach, I had something where I was just like taking the maximum of all the components, and then I was multiplying by like the size of the matrix for our estimate. This is a little bit slicker than that. All right, so there's that. And then with all this together, you asked why he made this definition for the norm of a matrix. It's pretty much because with all this set up, if you have L of x equals to AX, well, guess what? The norm of L is equal to the norm of A with this setup. And I'll skip the proof of that. All right. So let me just get to the kind of the takeaway point from all this for us today. And we'll have to circle back and probably take me about another half hour more to show you at least a sketch of the proof of the inverse function theorem in Rn. We should do that at least. But then I'll be on to like defining tangent spaces and normal spaces in higher dimensions, which is really cool and much more computational, much more easily testable too. But anyway, so here, the reason that I'm talking about all this mostly, well, partly it's a necessary setup for the proof I'm going over next class. But the bigger point I think is cool is if we look at F as a mapping from Rn to Rm, all right? And then the differential of F at x is what? It's an element of, well, his notation is LMN, which is a fancy way of saying linear transformations from Rn to Rm, if you had that notation in linear algebra, I don't know. But it's a linear mapping from Rn to Rm. That's the differential, right? And so really we can regard F prime, right, as a mapping from Rn to where? Well, to m by n matrices, right? Okay? And so, all right. And then he has this proposition. This is proposition 2.4 on page 176 of Edwards. It says this: the differentiable mapping F from Rn to Rm is continuously differentiable all right, at A in Rn, all right, if and only if F prime from Rn to, R m by n. His notation is not Rm by m. He writes this as a script m with a little mn down there. Like that's his notation for matrices. But anyway, it's continuous at A. And then he states, and then right after that, he states the mean value theorem for matrices, and it takes him about this half page of sorting through his various different concepts, probably applying the mean value theorem for regular calculus 1, and exploiting properties of the integral and everything to prove it. But this multivariate mean value theorem has been important to me in my research. Like I had to use that at one point critically for a proof of an existence theorem. Like that's something that comes up. It's good to know about that. This here, so let's see here. This continuously differentiable means that all of the partial derivatives exist continuously, right? And so if you look at what this is, right? Well, if you look at what this is, what are the component functions? What are the component functions of f prime? They're exactly the component functions of the Jacobian matrix. So it's not especially surprising that the forward implication is true, because like the component functions of this map are literally continuous if you're assuming continuously differentiable. But the reverse direction, if you have continuity of this, then that means that the component functions must also be. It's the vector limit theorem actually is what's going on here. I mean, that if you have a differentiable function, a vector value differentiable function, it's differentiable if and only if all of its component functions are differentiable. And in fact, continuously so. And so that's the reverse direction. And to prove it, of course, we'd have to use these kinds of estimates that we've been talking about in the other boards. And that's not really where this course is going. But I wanted to show you enough that you'd have a sense of like the kind of ideas. This book actually is interested in addressing that kind of nuance. It's not the best book, but it's a book. So anyway.
I'll see if I can access it.
Yeah, if you have any trouble with that, just tell me, because I can find it somewhere in my basement.
Are we in the multi
We're in the successive approximations and implicit functions chapter. That one, yeah. Very good.